So we usually represent an integer in decimal base, like 2017. This means what? This means 2 times 10 cubed, 1 times 10 plus 7. This integer is usually denoted like this for us. But there are different ways to do this using different base. Okay. So we use normally you usually represent integers in the decimal number system like this. System. But we can. There can be a different way of doing this. We will learn on that. Okay. For every non-negative integer n and b, integer b, b at least 2 or b equals 1 doesn't really say anything. Any integer n can be written uniquely this way as follows: n equals ck times b k, ck minus 1 times b k minus 1 dot dot dot, c1 b to 1 plus c0 b 0, where ci is an integer between 0 and b. We must have this. It must be strictly less than b. Cannot be like this. Like 2017 represented is 0 times 1 times 10, 7 times 10 to the 0, which is 1. So you can see these numbers are all between 0 and 9, less than 10. This is a b equals 10 case, but for any integer b greater than or equal to 2, we can say the same thing. And another common expression is binary number system. Probably this is very common in computer science. All right. So, example, binary number system. So 1 1 0 1 0. Usually we put like 2 just to indicate that this is in binary number system. So let's just for convenience, let's write the position of each number. So this is equal to here 1 times to the 4, 1 times 2 raised to 3, 0 times 2 squared, 1 times 2, 0 times 2 to the 0. All right? Now if you want, you can change this into the usual decimal expression like this. 16 plus 8 plus 0 plus 2, so it's 26. The 26 in base 10 decimal expression can be written as a binary expression like this. So converting some expression, representation base b into decimal expression is easy like this. You can always do this. How can you go backward? Like, suppose we have 26 in decimal expression. How can we change this into binary expression, binary number system? there is a nice algorithm. So how to convert decimal to binary. So 26, let's try to recover this. The idea is divide this by 2 like until we get 0. So let's write it this way. We divide 26 by 2. And the quotient is 13. I'm going to put the remainder here. The remainder is 0. This means I divide this 26 by 2, and this is the quotient. This is the remainder. And I keep dividing this by 2. Now the quotient is 6, and we have now remainder 1, and 2, 3, remainder 0, 2, 1, remainder 1. We do this until we get 0 for the quotient 1. Now you just read this backwards like this. So 1, 1, 0, 1, 0, which is the original one. Okay? This is how we convert decimal expression into binary. But this is not just for binary, anything. So let's do this with decimal to octal expression. Decimal expression to octal expression. This means 8 팔진법, if you want. So 475. So this is in decimal expression. We want to see what is this in octal number system. The idea is the same. You divide this by 8. What is the quotient? 5 here, 59. Remainder 6. 그러네요. 네. So the remainder is now 3. Now 8 times 7 equals 50. 56. Is that right? Remainder 3. 8, 1, 0, 7. So you just read this backwards. That means 7, 3, 3. This is always it always works, and then you can do this. Now we can add 2 numbers in any number system. How to add 2 numbers in base B. Base B means base B number system. I'm gonna just give you. But before doing that, let's review how we add 2 numbers in decimal system. We all learned this in elementary school. So how do we add 2 numbers like this? So first we begin from the last digit, and we add these 2 together. 3 plus 9 is what? 12. So we add a 1 over here and then 2, something like that. 12. We write this. Then we add these numbers. It's going to be 9. Nothing. We don't have to carry anything. So we say that we carry 1 to the next digit. We don't carry anything. Here it's 11, so we carry 1 over here, so 11. Now we add these 3 numbers, 12, so we carry 1 and 2. So it's just 1. So this is how we add 2 numbers in decimal number system. We can do this to the same thing for any number system. So for example, 3, 4, 0, 2 in 6, base 6. 5, 4, 1, 4, base 6. Let's add these two together. 2 plus 4 is 6. So it's greater than or equal to 6. We have to carry this. So we carry 6 to the next step. So it's going to be 1, 1, 0, right? 6 is 1, 0. 1, 0 in base 6. So we carry this 1 to the next. So now we add these all three numbers. It's going to be 2. There's no carry. 4 plus 4 is 8. 8 is what? 1, 2 in 6, right? 6 because it's 6 plus 2. So we carry 1 over here and then 2. Add this, again 8, so it's going to be 1 and 2, finally 1. This is base 6. So we can add things like this. Is this correct, by the way? Yes, that's right. Because, it was 9, not 8. 9, so it's 1, 3, so it's like that. Okay, so not that difficult, just quite similar to this usual addition. And now let's talk about some remainder again. So definition, we have two positive integers. Positive integers if a is equal to b q plus r, where r is an integer between 0 and strictly less than b, and q just any integer. Then we say that r is the remainder of a when divided by b. And q is called the quotient. The remainder, we are interested in the remainder because it's important. And we write this way. A mod b means the remainder, so it's going to be r in this case. And in computer science, I mentioned that this is also written like this, using this percent notation. But we will use this. A mod b means the remainder of a when a is divided by b, like this. So it has to be non-negative integer and has to be strictly less than b. So for example, 10 mod 3 is what? 1. 5 mod 7? 5. Minus 2 mod 6, what is that? Minus 2? 4. This must be between 0 and 6. So it's not minus 2, but 4. This mod notation is quite useful when we are interested only in remainders. So there is a theorem. So for instance, theorem AB mod k is equal to A mod k times B mod k. Do you think it's correct? This is not correct. I have to add one more. Mod k. Because this product of this can be bigger than k. We have to take the mod because we want this to be in the correct range. Proof is simple, so I'm not going to prove this. It's quite easy. So for example, like 2015 times 2017 mod 40. Suppose you want to compute this. If you compute the product of these two numbers, it will be very large. You can do this, but it takes time. So that means, so this theorem says you don't have to compute this. You just need to compute the remainders first. And what? We have to take mod 40. What is this? We know that 2000 is divisible by 40, so it's going to be 15 times 17 mod 40, right? What is this? Product of this? 255? 16 minus 1 times 16 plus 1 is 16 squared minus 1. But yeah, you don't have to do that. But so this is necessary because this is not in the right range. So this is what? 15. All right? So we didn't really compute this number. So similarly, maybe you can compute 17 raised to 10th power mod 7. Let's say we won't have this. It will be very difficult to compute this by hand. 2017 raised to 10th power will be a very big number. But we don't have to do that. This is 2017 mod 7 raised 10th power, and then at the end we can just take the mod. What is this? 2017 now divided by 7, 14. You can just do it by hand. 61, 7, 8, 56, 57. Oh, it's good. 8. Just 1. This is 1. Right? Very simple. We didn't compute this, but we obtained the remainder very easily. Any question? Okay. Then we're gonna move on to the next section. It's about some algorithm, famous algorithm, computing the greatest common divisor. The Euclidean algorithm. We know the definition of the GCD. Very easy. Greatest common divisor. We know how to compute this. We learned this theorem. If you have a factorization of both, this GCD is very easy. We learned a theorem that allows us to compute what? The GCD. GCD of Mn. If we know prime factorization. Right? Do you remember? Like M equals P1, A1, something like that. As long as we have this prime factorization, GCD is trivial, very easy. But the problem is, finding a prime factorization is not an easy problem. This is difficult. Finding a prime factorization is a difficult problem. Can you imagine this problem? Maybe you don't see why. 30, very easy. You can just 2 times 3 times 5. We just did it very easily. I'm talking about prime factorization of a large number. If the number is small, like 24, something like that, this is not difficult. But what if the number is very large, like 2017 and 2015, they attach it together, like 2000, I don't know, this big number. Can you find the prime factorization of this? It will take a lot of time, even for computer, if the number is large. So you have two numbers. If you want to use that theorem, you have to find the prime factorization of this, prime factorization of this. They are very difficult. It will take a lot of time for computers to do this. But there is, fortunately, there is a better way to do this. We don't need prime factorization. A Euclidean algorithm is like that. So for instance, maybe this is too large, so you cannot really imagine it. But so for instance, 2021, 2023, 3. Can you find the GCD of this? If you want to use that theorem, you need to factor this into primes. Can you do that? You can do this, but you need time. You have to, they might be prime, I don't know. Can you see a prime factorization of this? I've heard that there is some people whose hobby is factorizing four digits. Like if you go to some plate on a car, he just factor that into prime. Maybe for those people, they can factor this easily, but for us, it will take some time. We have to try to divide this by 2, 3, 5, 7, until we get something that divides this. It turns out that this is 43 times 47, but can you find this? It will take some time. And this is 47 times 49. If you know this, of course, the greatest common divisor 47. Easy, but we don't know this. We don't know this. It will take time for us to do this. So we need a better way than this. And there is a nice theorem. Suppose we have this. A equals BQ plus R. A greater than equal to 0, B positive, and R is the remainder, so R must be 0 and less than B. Then GCD of A comma B, GCD B comma R. This is the main idea of the Euclidean algorithm. Proof is not difficult. We will show the following. The common divisors of A and B are exactly those of B and R. A, B are exactly the common divisors of B, R. They are exactly the same. Do you think this is enough to show for this? Suppose that this is true. We have the same set of common divisors. So what does this mean? It is the largest among these, right? This is the largest among these. And they are the same. So the largest must be the same as well. This is the idea. So we will show that common divisors are exactly the same. Okay? So what does a common divisor mean? It is an integer that divides both A and B. So suppose D is a common divisor of A and B. What is R? R equals A minus BQ, right? D divides A, D divides B, so D must divide this, because it's a multiple of D, sum or subtract difference of multiples. So D divides R. But we already assume that D divides B, so D is a common divisor of R and B, right? This implies this. Common divisor of AB is always a common divisor of B and R, like this. The other way is also simple. Suppose we have a common divisor of B and R. We need to show that it is also a common divisor of A and B. What is A? PR BQ plus R. This is divisible by what? D. D. R is divisible by D. So their sum must be divisible by D. So A is divisible by D. But we already assume that B is also divisible by D. So it's common divisor of A and B. It proves this thing. They are the same. Okay? Since GCD AB is the largest common divisor of AB, this is the same of what? B and R, because they're common divisors. These are exactly the same. This is GCD of BR. All right? Any question? Okay, so we have proved this theorem, but do you think this is useful? Why is this useful, do you think? So our goal is to find the GCD of two numbers. The problem is, it's difficult when the numbers are big. If the numbers are small, finding GCD is easy. But what does this say? What does this say? Which one is bigger? You know, let's say A is big. A is bigger, big, and if you divide A by B, R is smaller than B, right? So this part, B and R, the numbers will be smaller than A and B. This means we can decrease the size of numbers. We can keep applying this theorem again and again and again, and we will eventually end up getting very small number. And that will be the GCD that we want. Okay? So let me give you the precise algorithm. So this is basically the Euclidean algorithm. The idea is to decrease the numbers by using that theorem. Very efficient way to compute GCD. So input AB, non-negative, not both 0. Output, of course, GCD. Okay, let me write down the pseudocode GCD A comma B. All right? We will use the previous theorem, A equals BQ plus R, then GCD of AB equals GCD of BR. This is the theorem before. Now, maybe A is bigger or B is bigger, we don't know. Let's see, we want to have A larger. If not, then we will change that. So if A is smaller, then we will swap A and B. This means we will assume that A is bigger, A is the big one. So, okay? So now after this, A is big. Now while B is non-zero, we will do the following. R equals A mod B. We are basically doing this thing. R is what? The remainder of A when divided by B. So it's A mod B. Okay. All right. Now we are considering this. We will change that into this. So now what? The first number, so A is the first number, B is the second number. What is the first number now? Here, b. So we will set a to be b. We replace a by b. The first integer is going to be b. The second integer is going to be what? R. And then we repeat. We repeat this until the second integer becomes 0. So because the a is the first integer, b is the second integer, we do this until b is 0. What happens if b is 0? Okay, let me write this and then return. We're going to return something. All right. What happens if we have b equals 0? What does that mean? At some point, we will have a comma 0, this thing, right? In this case, we don't do this. We will exit this while statement. What is the GCD of this? A comma 0. 0 is a multiple, and everything is a divisor of 0. So A is a divisor of 0, so this is A. GCD of A comma 0 is always A. All right? Because A is a divisor of A, of course, and it is also a divisor of 0. 0 equals A times 0. So something, GCD of something comma 0 is always something, that thing. So we're going to return A. This algorithm finds the GCD very quickly without doing prime factorization. Because the number decreases very quickly. Like, is this okay? Any question? This means A, the first A, you should think A as the first integer and B as the second integer. First integer is now replaced by B. The second integer is now replaced by A. And then we repeat this until we obtain something comma 0. When we get something comma 0, GCD will be the first integer, A. That's what this algorithm says. All right, let's see if we can really use this. Okay, I showed you this example. Let's try that example. Where was it? GCD 2021 to... Let's see what that algorithm does to this. So this was A, this was B, right? This is A is 2021, B is 2303, right? A, which one is bigger? B, right? B is bigger, so we swap this. So this is equal to GCD to 303 to 2021st. We swap this. Now, this is not 0, so we divide this by this. What is? Okay, so after this, we move this front. And what is the second one here? The remainder of this. What is the remainder of this when divided by this? 2000, this is equal to this plus 282. Is that right? Yeah, I think I chose two big numbers, but anyway, we can do this. I want to show you we can do this. Please correct me if I made a mistake. If I make a mistake, I didn't compute this before, so it's very likely that I will make a mistake. So now GCD still not 0, so this goes front. Now we're going to divide this by what? 282. What is the quotient here? 7, 14, 57, 19. Okay, good. 7, 47? Oh yeah, we are good. We already know that this is the answer. So now what? We have to move 47 front. We have to divide this by 47. So what is that? 6. Exactly this. Going to be 0. So GCD is 47. This is what the Euclidean algorithm does. All right? We don't even know that at this point whether this is prime or not. It doesn't matter. We just found it. This is very easy. All you need is just some division. We didn't do any factorization. Very easy. Any question? So if you are given two big numbers and if you want to compute the GCD, you should use this. Okay, there is an interesting theorem. Let's say we have non-negative integers, not both 0. Then there exist integers s and t satisfying GCD a comma b equals s times a plus t times b. This means GCD can be written as a sum of multiple of a and multiple of b. This is a multiple of a, multiple of b. By choosing s and t carefully, you can always express this as a sum of two multiples. I'm not going to give you a precise proof of this, but Euclidean algorithm kind of give you the idea why this must be the case. I'm going to explain the reason behind this theorem using Euclidean algorithm. So, for instance, we can construct T and S and T. Euclidean algorithm allows us to construct S and T. So, GCD of 38, 52 is 2. This means there must be something 3 times, T times, let's use A first. S times 38, T times 52 equals 2. We can find two integers S and T satisfying this relation. How can you do that? If you try to plug in some numbers, then it will take a lot of time. Can you find by looking at this? We need to try many times. But Euclidean algorithm gives us a method, gives us a routine to compute this. So let's do this. So first, we do as Euclidean algorithm does. So we divide this, the bigger number, by the smaller number. What is the quotient? It's 1. 1 times 38 plus what? 14. Okay? Now, the GCD of this is equal to GCD of this too. So we divide 34 by 14. 14 times what? 2 plus 10, right? Now we divide 14 by 10. 10 times 1 plus 4. Divide 10 by 4, so 2 times 4 plus 2. Now divide 4 by 2. 2 times 2 plus 0. So now finally we obtain 0. So the GCD is 2. Oh, by the way, this means this is the GCD. The previous one must be the GCD. Now, our goal is to express 2 in terms of multiple of 38 and 52. How can you do that? We will reverse this. Here, if you look at this is expressed in terms of 10 and 4, right? Is 1 times 10 minus 2 times 4, right? I just rewrote this. Now, if you look at this, 4 is written in terms of what? 14 and 10, right? So here, 4 is equal to 14 minus 1 times 10. Here, 10 is equal to 38 minus 2 times 14. Here, 14 is equal to 52 minus 1 times 38. So, we can replace 4 by this, right? And then we can replace 10 by this. We can replace 14 by this. We will eventually end up getting only 52 and 38. Okay, let's do that. So here I'm going to replace 4 by this. 10, 1 times 10 minus 2 times 10. What is this? 14 minus 1 times 10. And I'm going to simplify this. You know, here we have, let me write 14 first. Minus 2 times 14. Here, this is 2. 2 times 10, we have 1. So it's going to be 3 times 10. Okay? We consider these as like variables or just letters instead of numbers. I'm not going to compute this right now. I'm going to keep expressing the numbers in terms of other numbers. Okay? Now, what is 10? I'm going to replace 10 by this. So let me continue over here. Minus 2, 14 is still the same. 3 times, what is 10? 38 minus 2 times 14. Now, let me simplify this. 38 goes first. Now, minus 2 minus 6. So it's going to be minus 8. Is that right? Yes. All right, now what's next? Express 14 in terms of this. Replace 14, so here. 14 equals 52 minus 1 times 38. So it's this one, 1 times, this is 8. 8 plus 3, 11. 38 plus minus 8 times 42. We express 2 in terms of 38 and 52. So what is S here? S equals 11, T equals minus 8, and we obtain this. Okay? This always works, and this is basically explains why this is true. We can construct S and T in this way. Do you think you can do this? All right, now we need to define one more definition. What is the inverse of something? You know, what is the inverse of x for a non-zero number x? Real number. What is the inverse? X inverse. Usually we denote this by this. What does this mean? Okay, so 1 over 7. What is this? What does inverse mean? Here we kind of omit it, but inverse of this, we here multiplicative inverse. We consider the inverse of the operation, multiplication operation. What is the inverse of something according to some operation. This means, inverse means, the integer or number that if you multiply this to x, then we get the identity. Multiplicative identity is 1, right? If this happens, then we say that this is the inverse of x. So 7, for instance, 7, this is 7 inverse because what? 1 times 7 equals 1. This is the reason why we call this the inverse of 7. But this is a real number or rational number. Do we have the inverse of 3, multiplicative inverse 3 in integer? What is the multiplicative inverse of 3? 1 over 3. This is not an integer. So we cannot really talk about inverse of in integers, right? Because it's not there. 1 over 3 is not there. But we still want to talk about the inverse of an integer, which is also an integer. But of course, we have some obstacle here. There is a way to kind of avoid this obstacle by defining the inverse in a slightly different way. So n is greater than 0, k is greater than or equal to 1. I'm not sure why I wrote this. They are the same. They are just greater than or equal to 1, positive integer, let's say. Then the inverse of n mod k, not just n, inverse of n, but we consider mod k, is the integer which is in this range, greater than 0, less than k, with this relation, n mod k equals 1. This is the definition. Do you see? So this is the inverse of n mod k. Because we cannot really have the usual inverse, we have to take mod k. Everything is mod k. What does that mean? We only look at the remainder when divided by k. So a times n is of course not 1. It will be bigger than 1. But if we divide this number by k, the remainder might be 1, right? If that happens, then we say that a is the inverse. But we must have this so that the inverse is unique. Okay, but before, inverse not always exists. There exists the inverse of n mod k if and only if, this means if and only if, their GCDs are 1. They are relatively prime. This means GCD is 0. So for instance, the inverse of 7 mod 9. Let's compute this. This is 4, in fact, because 4 is between 0 and 9, right? And what is 4 times 7? 28. This mod 9 is what? 1, right? So 4 is the inverse of 7 mod 9, because 4 times 7 equals 1. The remainder is 1 when divided by 9. All right? This is the definition of inverse. So we kind of change the definition of the inverse slightly so that we can really have integers there. But inverse does not exist. Inverse of, say, 4 mod 6 does not exist. Why? 4 and 6, they are not prime, not relatively prime. The GCD is not 1. So 4, can you find something? 8 times 4 mod 6 equals 1? No, because 8 times 4, this means equals 6 times k plus 1. But this is in other integer. This is even, this is even, this is odd. We cannot have this. So if this is not 1, it must be a multiple of the. This must be a multiple of the greatest common divisor. So if the greatest common divisor is not 1, we cannot find the inverse. Any question? All right. So the question is, how can you find the inverse? Here you can just try some numbers. Actually, the inverse, if there exists, must be one of these: 1, 2, 3, 8. You can try 1 there, 1 times 7 divided by 9. The remainder is not 1, so we have to go the next one, 2. In this way, you can find, of course, the inverse, but it takes a lot of time. We need a better way to do this. This is okay for these small numbers, but when these numbers are large, this kind of approach is very time-consuming. All right. But Euclidean algorithm also, the same thing works. Because we are basically finding something as before. What did we do over here? We expressed GCD in terms of multiple of A and multiple of B. GCD equals 1. We express 1 in terms of this. This will give us the inverse. Okay? Let me explain more in more details. So the problem is this. Find the inverse of 48 mod 13. Okay. Solution. We need to find what? Integer a such that a times 48 mod 13 equals 1, right? This is the definition. But of course, we must have this. But let's focus on this first. What does this mean? This means a times 48 plus k times 13 equals 1 for some integer k. Is that right? This is exactly what the remainder says. We divide this by, okay, maybe I should write this way. They're the same. This is exactly what this mod means. We divide this number by 13. The remainder is 1. Okay? But this, if you remove this other side, minus k, but okay, let's write minus k equals 1. We want to find an integer a satisfying this. But this is something that we already saw. This is the GCD of two numbers, right? We want to express GCD as a multiple of 14 and 48 and 13. We did this before. So we're going to do this. So let me tell you how to do this. We want to find the GCD. So 48, we divide this by 13. 13 times what? 3 times 13 plus 9 is going to be this. Okay? Now we divide 13 by 9, so 1 times 9 plus 4. Now we divide 9 by 4, like this. And actually we don't have to go further because we already found 1 here. 1 is the GCD. Now we are going to express 1 in terms of this and this. So now what is 1? From here, 1 is 9 minus 2 times 4. We are doing exactly the same thing. Now what is 4? 13 minus 1 times 9. Here. So this one, we can replace 4 by this. 13 minus 1 times 9. Okay. Now simplify this. Let me continue over here. Minus 2 times 13. This is 2. 2 plus 1. So it's 3 times 9. All right. Now what is 9? 9 is 48 minus 3 times 13. So replace 9 by this. So if we simplify this, it's going to be 3 times 48 minus 2 minus 9, so minus 11 times 13. Okay? Now we found A, which is 3. So A is, in fact, this. This thing is going to be A. 3 mod 13, which is just 3. This is the answer. The inverse is this. Because 3 times 48 mod 13 equals 1. This is what, let's say. It is important to take a mod 13 at the end. In this case, it doesn't make any difference, but sometimes it is a big difference. For instance, I'm going to do the same thing with their roles are reversed. So I'm going to do this in the next page, but any question before I move on to the next page? All right. I'm going to do exactly the same thing with their roles, change it. Okay? So example, find the inverse of 13 mod 48. What do we need to do? We need to first find something. A times 13 plus B times 48 equals 1. We need to find this. But we already did that, so let's use that thing. We already found this in the previous page. 3 times 48. We just showed that we have this. What is the inverse then? What is the answer? You cannot simply write this. It's not going to be minus 11, but it's going to be minus 11 mod what? Mod this. Mod 48. What is this? Because we want this to be in this correct range. Minus 11 is not in this range. We want this to be in the correct range, and we can do this by taking mod, the remainder. What is the remainder here? You just add 48 there, then 37. That's this, correct. This is the final answer. Okay. So Euclidean algorithm is not only useful for the finding GCD, but you can also use to find the inverse, mod something. Without using Euclidean algorithm, this can be a very tough problem. You need to consider many, many cases. But using Euclidean algorithm, it is kind of routine.